Hello and welcome to the first joint session of the triple conference DAGM GCPR VCBM and VMV 2020. It's my pleasure to share this very first joint session. My name is Hendrik Lensch, and we're going to start right away with one talk from the, or with two talks of the GCPR, one talk by the VMV and one talk organized by VCBM. And the first talk is by Felix Draxler, Jonathan Schwarz, Christoph Schnörr, Ullrich Köthe, all from the University of Heidelberg. Please go ahead. And just one more thing, please use the Discord channel, which you find in the program, in order to ask questions, which I'm then going to assemble and ask at the end of the talk. Thank you.
Okay, thanks a lot for the kind introduction. To start off, I want you to think about a generic machine learning problem. So you should approximate the mechanism. So you're given an input X and you should output the corresponding Y. And I will guide you through this with an example of image colorization. So you're given a grayscale image and should predict the color channels. And there's basically two types of models that you can come up with. And the first one is a deterministic model that will just predict the single best response. So for example, the one that is most likely could be this bird, for example. However, the world is not deterministic. There might be noise, there might be ambiguity. And to cope for all these kinds of uncertainties, in some situations, it might be helpful to actually use a probabilistic model that models the full posterior distribution of all possible outcomes. And this way, you can get a whole lot of differently colored birds. This concrete application will be shown by my colleague Linton on Thursday at GCPR at 9 a.m. And today we'll be talking about probabilistic models, and one model in particular, which is called normalizing flows. Normalizing flows work as follows. So we're given a data set and that stems from some yet unknown distribution, mu of x, and we want to approximate this mu of x. And the way normalizing flows do it is that they reshape the data so that they are normally distributed. And then we apply the inverse function so the t of x is learned, t to the minus 1 of z is then applied. And this way we can reconstruct the target distribution that we were aiming for. Now, how can we represent such an invertible function? One way to do it is with neural networks that are constrained to be invertible. So a popular architecture is the real NVP architecture. It's popular because it's equally fast both in forward and inverse direction. And it also has fast access to the Jacobian determinant, which we need to actually evaluate mu of x for a given point x. It's a deep flow, which concatenates multiple so-called affine couplings or real NVP couplings. And there's many ways to represent invertible functions. Another one is given by my co-author Jonathan tomorrow at 11:15, also GCPR. But back to affine couplings. So affine couplings consist of two parts, and we'll talk about the second part first. This is called we call it the nonlinearity, and it takes a part of the dimensions, which we call the active dimension, and change it, but leaves the other half unchanged. And this makes it really easy to invert. So this is the function up here that we learn, and this is super easy to invert if p is the same in forward and backward mode. Now and in total you see that this is an affine transformation. So for each p we can modify the whole stack of a's by moving them or by moving them further apart from one another. Okay, but note that we cannot, with such a coupling, we cannot represent arbitrary nonlinear dependencies on P and A, like this function here. Now, if we stack several such affine transformations and always keep the same active and passive dimensions, then this would be just another simple affine transformation. So what we do to represent complex functions, that each layer chooses these active and passive dimensions differently. And we do so by rotating the data before it is passed to this nonlinearity. And this rotation determines active and passive dimension. Now, these transformations look pretty simple, but somehow in practice, we are able to represent really complex distribution. Now, how is this possible? And in this work, we give a part of an answer to this question by finding the global minimizer for the building block of a deep flow. So we don't consider a deep flow, but we consider just a single coupling layer coupled to the default loss. Now, using this minimizer, we can then derive the loss improvement that is possible by a single layer as a function of this rotation before the layer. And this, again, we can use to build a deep flow in a layer-wise manner. So let's get started. So what does a real MVP layer learn at the global minimum? Well, what it does when it is coupled to maximum likelihood loss, which is the typical loss for normalizing flows, it learns the mean and the standard deviation of the distribution of A's for each P. So here I have an example. We have this distribution up here, which is a uniform distribution along P and a normal distribution along A. And for each value of P, we have a different mean and standard deviation for this normal distribution, just depicted here. And if we now learn this single layer, coupled to the maximum likelihood for this distribution, so using samples from this distribution, we can directly read off this conditional mean and standard deviation for each P correctly. And then the effect of this layer is that it whitens the data for each P. So we subtract the mean for each P and divide by the mean so that all 8 distributions have the same form in this example. Now that we know the minimizer, we can also evaluate the loss at the minimum. And there will be a formula which you will see in a second, but you don't need to parse it. I just want to show that we have it. And what is more interesting is that we can actually subtract the loss before the layer from the loss that we have after training this layer, and derive a closed form expression for the maximum loss improvement that is possible by the layer. And this then depends on the rotation Q, as I said. So how does this formula look like? Well, there's a contribution from fitting the mean correctly, so this one, and there's a contribution from fitting the standard deviation. Now, this entire expression can actually be approximated at least directly from the data. So there is no need to train a network to know what the maximum loss improvement will be after training. So we can directly from the data read off like this conditional mean, for example, by binning the data for the different values of P and then computing the mean and standard deviation empirically. And notice that there's a strong dependence on Q here, although it's not explicit. So the Q is hidden in the choice of A's and P's, as I said previously. Now that we know for a certain rotation Q what the maximum loss improvement will be, we can use this to compare different rotations. So we can solve this optimization problem where we want to choose the rotation so that with one single layer we can maximally reduce the loss. And if we here compare different rotations, we see that there's one rotation that really hits it off in comparison to the other ones. And what you also see that this is a tight bound, what we computed, so the loss curve actually achieves this bound. And now we can apply this for layer-wise training. So think of end-to-end training where you fix the number of layers beforehand, and then you draw random rotations QL before training. And then you train it and obtain some flow that in the end hopefully approximates the distribution you were looking for. Now with our theory, we can make layer-wise training more efficient. Layer-wise training means that we add layers on the fly and only train the last layer that we add. So we kind of work our way from the residual to the on the residual, right? And this is cheaper, or can be cheaper, because we can simply stop when we're satisfied. So we got rid of this hyperparameter of the number of layers, and we don't need deep backpropagation, which can be unstable. And using these optimal rotations, we can actually speed this process up. So if you look at, so in these two lanes, we now compare random rotations to those that resulted from maximizing this loss improvement. And you can see that we can be lucky with the random rotations and have the same or comparable quality to when we optimize the rotations, but we also might be unlucky and there's not a real progress by a single layer if this rotation is not meaningful. So, and in this particular case, we actually achieve the same quality as the end-to-end network with 4 layers after 3 layers. And also note that this flow is a lot more sensible. So if you look at the shapes that we obtain up here, they're rather extreme and have extreme values for the probabilities, but here we kind of converge towards the normal distribution that we were looking for. But at the same time, layer-wise training has its own drawbacks. And so for random rotations, in this particular case, it doesn't even really converge to a good solution. how does it compare number-wise? So optimal rotations, we find them to be always better than random rotations. But once we reach a certain depth, they kind of have a comparable performance. But note, so this doesn't look like a big step, but the important thing is actually looking at the in this direction. So to achieve the same quality for the blue curve, we need 4 layers comparison to 2. So that's kind of a factor of 2. But at the same time, end-to-end training is typically on par once we go to more than 2 layers. And then later it's better. Now, obviously there's a gap to end-to-end training. So layer-wise training still lags behind. And I mean, it's kind of obvious because our theory only considered how we can treat a single layer. So probably this wasn't even to be expected. And the reason will be that interactions between layers are ignored. So we started with training 1 layer, then we froze that layer and learned the second layer. So there's like no interaction. And as a compromise, we suggest that one should add layers 1 by 1, but propagate the gradient back to the previous layers. So we start with 1 layer, and when we train the second layer, we also train the first layer. And in this way, we can still choose optimal rotations, although they will later on, of course, not be governed anymore by the theory. And I just want to show you a quick example in the remaining time. So let's check out this checkerboard pattern here. And if we do layer-wise training with optimal rotations, this is what we get after 4 layers. And if we do this progressive training, so this is compromise, we improve a lot, and we also improve over progressive training with random rotations. So the structure is a lot better represented here. So to sum it up, random rotations and fixed depth end-to-end training, that's what was previously possible. And now that we know the role of a single affine layer, we could actually derive a formula for these optimal rotations. And this improves cheap and stable layer-wise training, although it doesn't reach the quality of end-to-end training yet. And we obtain more reasonable flow with this, and we can reach end-to-end quality using progressive training and optimal rotations. As a next step, we propose to treat layers that interact so that we can hopefully surpass end-to-end training. And it's also open how we should evaluate this loss improvement in high dimensions. Thank you for your attention.
Yeah, thank you very much for this very nice talk, giving some theoretical background on how to do optimal flow and transport. There are already a couple of questions piling up in the Discord. If you have further questions, please put them in there. I start with one very brief one. You already indicated that your stepwise optimization layer by layer does not necessarily reach the same accuracy as the end-to-end training. Could you briefly indicate what is missing? I mean, in the pictures you showed, we see that for the end-to-end training, intermediate step seems to be a little bit more, broader in what's happening, while the layer by layer approach sort of like is more tuned down and doesn't have extreme transports in there. But what's happening if in the end-to-end, which you cannot cover with the stepwise?
So I think the end-to-end, so these artifacts in end-to-end stem from those rotations being like really close together, or like just not really matching to one another. That the network has to push things very far apart or very close together to actually represent complex shifts. So this is what we hope to improve by optimizing these rotations. And I think what is still missing is that so we can only change one dimension at a time. As I said, like in this 2D example, at least we can change one dimension, the other one is left intact. So if we, for example, want to represent a function where both need to be changed in a nonlinear fashion, then this is something that we can only do if several layers interact. And then it could be possible that the role of one of those layers is becoming different from just like reducing the loss, but it should also prepare the distribution in a way like pulling things apart in the first step, and then in the second step rearranging them in a way reduce the loss. Yeah.
But another question that was asked is it really a problem for end-to-end training if some of the intermediate representations do not seem to create meaningful shapes? I mean,
So I think for end-to-end training, if you're just happy with the, like, if you just look at the quality of the representation in the end, of course, this is something that is not important. But so I think one point is that layer-wise training can really, like, you always have a good representation. You can stop when you're satisfied. So this is the big advantage of layer-wise training. And I think if you really want to understand how these networks work, then you need to understand how intermediate representations should look like. And I would simply argue that these extreme representations are probably not the answer.
Okay. And another one is the theory you've presented here, you've shown and explored on relatively nice examples where one can easily see what's happening. How does it apply actually also for conditional coupling blocks, like we've seen, for example, in Vito Ferrari's nice talk yesterday on 3D analysis?
So the problem for this theory in here is that the condition has to be accounted for in this estimation, or we have to. This is basically what I said here is that we. Anyway, so what I said is that this evaluating this delta of Q is difficult when you have more passive dimensions, and the conditional dimensions, they just add to the passive dimensions. So the dimensionality for this estimation is a lot more difficult. But we do hope that solving this optimization problem is also possible when we have more passive dimensions. For example, so the current thing we do is that we bin the data in the passive dimension, and this is certainly not possible if we have many dimensions, but there might be other approaches.
Okay, great. Thank you very much. And then we should go on for the next talk. And I would like to ask Max Losch to set up while you close your stream, Felix. Thank you again. Okay, great. And now I guess you can start sharing your screen.
Good morning.
Morning.
Can you hear me?
Okay.
All right. Yes, you can.
Great. I'm happy to introduce the next speaker. That's Max Losch, together with Mario Fritz and Bernt Schiele, all from Saarbrücken, from the MPI, as well as from CISPA, have this interesting talk for getting sense from deep representations by introducing semantic. Please go ahead.
Thank you very much. And yeah, good morning again. So my name is Max, and I'm presenting our work on semantic bottlenecks, a method to improve the inspectability of deep representations by producing efficient codes. As I already said, this is joint work with Mario Fritz and Bernt Schiele. So consider a well-performing deep convolutional network here, for example, on street scene segmentation. One of the critical issues that is obstructing interpretability is the fact that if we look at intermediate representations or activations, they're generally in the hundreds of thousands of channels, and all of them are generally highly distributed, such that each of these channels are very difficult to interpret since they have unknown semantics, or at least their semantics is not clear to us humans directly. Let's have a look at in a couple of examples here for this particular network. If we look at one of these channels, then we can see that there's a strong activation for the upper torso of persons, seemingly suggesting that the semantics of this particular channel is something related to persons. But we can also see that in the upper region there are strong activations for the sky. And the connection to be made here is very difficult to see what the consensus in terms of the concept is. Another channel would be, for example, here, where we again have activations for persons, but here very incoherent to different regions of persons. And another channel where we again have activations for persons and also seemingly for vertical edges. But all of these channels are generally difficult to align with a particular semantic. So since looking at individual channels is a bit troublesome to get the whole context, we can aggregate these channels and have a look at all of the other layers by color coding them and ranking them based on their activation magnitude, such that we get some color-coded image like this. So, but this is further evidence that these intermediate representations of standard deep conv-nets are very difficult to interpret, since they have no good alignment with the semantic concept, and they're highly dispersed across different regions in the image space. So this brings us to the motivation that we directly want to improve the inspectability of intermediate representations. And for this, we state 3 simple goals. This is, first, we want to reduce the number of channels to a minimum, right, from thousands to just a couple of tens. And secondly, we want to align each of these channels to a particular semantic that is more meaningful to humans. And all of the 2 former goals should not impair the classification performance. Right, so given these 3 motivation goals, we propose the use of semantic bottleneck layers. That is very simple linear layers that we can integrate into any kinds of architectures and models that are either pre-trained or not pre-trained, and that enables the alignment with semantics and also heavily reduces the number of used channels. So that if we would color code it again, that would have much more coherent activations, and it's easier to identify particular concepts relating to each of these channels. So in fact, this image that I'm showing here is the result of applying our unsupervised variant of the semantic bottlenecks, which I will introduce now. So we explore 2 variants of the semantic bottlenecks. The most intuitive one is the supervised semantic bottleneck version. Here, each of these channels of the semantic bottlenecks is supervised with additional annotation, such that each channel is aligned with one particular semantic concept. So these visual concepts can be taken from all kinds of data sets, but generally, of course, they should be related to the target task at hand. And given the example from before, like street scene segmentation, here in this case, again, we could use something like parts of objects or materials or textures. So since this annotated data is hard to come by, just for the sake of interpretability, we also explore a second variant that is the unsupervised semantic bottleneck, as was mentioned before. And since we cannot explicitly supervise each of these channels now with regard to a particular semantic, we apply here, or we enforce these unsupervised semantic bottlenecks to have one-hot encodings at the output. So we will show later that already using one-hot encodings is enough to strongly improve on the semantic alignment. So the method here is fairly straightforward and simple, right? So the question is, how do we get one-hot encodings at that particular layer? So we start off again with a linear layer, apply a softmax nonlinearity with the standard temperature of 1, and then anneal the temperature during the course of the training to close to 0, such that we approach the argmax in the limit of the at the end of the training. So that during inference we can actually replace the softmax with the argmax and thus get actual one-hot encodings. So let's have a look at a few qualitative examples from these unsupervised semantic bottlenecks. At the bottom here, we can see that this particular channel has fairly crisp semantic alignment, right, with regards to the buildings, or another one that is with respect to persons, or another one that has strong alignment with bicycles. Right under the top layer, again, we can see the individual activation maps from a particular layer of the regular resonance, and here it's much more difficult to identify a particular concept. So all of these qualitative examples are, of course, great, but one thing that's always a bit limiting in terms of interpretability is that we want to quantify how interpretable a particular layer or how interpretable a particular model is. And this is why we've also proposing an interpretability metric that we call AUIC. And this is inspired by a related work, Network Dissection by Bau et al., that was published at GCPR in 2017. But we improve on their metric by rendering it model agnostic and making it independent of chosen hyperparameters. That is a bit of a crux in the original proposed metric. So the question, of course, becomes, so how do we actually quantify interpretability of a layer? So we start off by quantifying the interpretability of particular or individual channels. So the fundamental idea is that we consider each activation map or each channel as a binary detector by looking at the activation map for a given image, by thresholding it to a binary mask, and then comparing it to a set of visual concepts or attributes that are predefined in an annotated given set. So we perform this for all possible thresholds and choose now the concepts that has the best alignment. So in alignment here, in our case, we mean the intersection over union. So for each pair of concept and channel, we evaluate the intersection of unions and take the threshold that maximizes this intersection of a union. Right. So since this intersection of a union gives us only a glimpse of how interpretable a particular channel is, we still have to aggregate these values for a whole layer, and this is how we construct like a single scalar quantity that we call AUIC. And the fundamental idea here is that we count how many channels we consider interpretable when we consider an IOU threshold phi, right? So given an IOU threshold phi, let's say 0.3, then how many channels have an IOU that is greater than 0.3, right? Then we would get in this particular two-dimensional plot, we would get this point in this plot. But since that particular threshold phi would then be very specific again, we calculate the same quantity for all kinds of IOU thresholds, such that we would get such a curve, and by integrating under the curve, we would we acquire the AUIC. So this AUIC is then our scalar metric that we can then compare our models with. So just to give an overview, right? If none of the channels are interpretable at any point for any threshold, this would mean that we have very poor inspectability. And if all of the channels are always considered interpretable no matter the threshold phi, then we have great inspectability, right? So then we would get an AUIC of 1. So what our metric also gives us is a second dimension of interpretability. If you remember, we have chosen the maximum threshold theta, but that particular choice is or does not need to be stable, right? So the question becomes again, besides how well a particular channel is aligned to semantics, how stable these semantics are with respect to the chosen threshold theta. So in the general case, usually what we see is that the activation maps are generally, sorry, I'm looking for the mouse here, but I can't see it. That there are general multiple regions in the image where a particular channel activates or responds to. So given here in the example on the bottom right, this is an example of a low stability channel, right? So it's very inconsistent to a concept. There's activations for the bike, but there's also activations for the tree and so on. So ideally, you would like to have a concept that only activates for one particular concept. And just to take a few steps ahead and just give you a glimpse of the problem here is that if we calculate this stability and put it in contrast with our AUIC, then the original representations have a very, very low value for stability. The SSBs, the supervised semantic bottlenecks as well. And only the unsupervised semantic bottlenecks have a very high value since they are binary in the output. So going back to the semantic alignment, right? So going back to the results, we have now all parts together to conduct the quantitative comparison between our semantic bottleneck and the baselines. And here in this case, as was already introduced in the previous slides, we are utilizing street scene segmentation, namely cityscapes, and we're using the model PSPNet. So, and for the supervised semantic bottlenecks, we are sourcing our data from the broadened data set that was also published in 2017, that is a collection of over 1,000 different visual concept sets from 8820K, Pascal parts, and so on. So I show here two different positions of introducing semantic bottlenecks. That is at an intermediate layer, namely the residual block 4 in the PSP.NET, and also a late layer that is after the pyramid pooling layer. And we perform our quantification for two different visual concept sets, namely cityscapes parts and broaden. And each of these two-dimensional plots shows on the y-axis the mean IOU. So this is the classification performance of the PSP.NETs on cityscapes. And on the x-axis we have the area, so the AUIC, our interpretability performance. So the first thing I want to note is that considering the original presentations in red, the dots and reds, we have channels, we have number of channels of 1,024 or 4,096 respectively, and our SSBs and USBs put them way below under 100. Even for the late layer, we have 36 channels with respect to 4,096. So, first observation is that we have little to no performance impact despite the channel reduction. And the secondary, of course, the most important one, is that we have up to 4-fold inspectability gains by using supervised semantic bottlenecks, but also unsupervised semantic bottlenecks are surprisingly effective in that regard. So just repeating the qualitative examples that I've already shown before, we can see that no matter whether using SSBs or USBs, we get much more coherent representations that are more aligned to visual semantics, and those get more refined in the later layers. So to conclude, so we have achieved our 3 goals, but importantly, I think we offer a quantifier baseline for interpretability, something that we think is in dire need for the topic of interpretability. So I take questions, and thank you.
Yeah, thank you very much for this very nice talk. There has been a very positive comment already in Discord that this technique might be very useful for explaining what is actually happening also in deep learning networks in the medical community. Mm-hmm. How do you think, how difficult it is to find also the visual concept and in this completely new domain? You had here clearly worked with predefined concepts which were there, and then this has been automatically selected, but how can you go for other domains?
Yeah, so for other domains, of course, the crucial aspect to actually quantify is to have a set of visual concepts. So you do need a set of pre-annotated concepts. The good part is that you don't necessarily have to have a large set of concepts. So in our case, for example, we evaluated a small data set of just 11 images for which we annotated cityscapes based on their parts of objects. And you can, so we got actually quite consistent results with such a small data set. But again, so this would be the bottleneck for other domains.
Okay, so this needs to be done. Good. Another question that came up is if the specific layer is optimally interpretable, it matches its activations with the semantic, then the question is why to continue to process later layers as well? Once you know that in the network or distances has been extracted, why do you care about potentially looking at the same things?
Well, so that depends on the concept set that you have evaluated the inspectability for, right? So if you evaluate the inspectability for the target domain at hand, then of course, if you have perfect interpretability, then you would also have perfect classification performance. So, but this isn't exactly what we were specifically looking into, right? So we were looking into whether deep representations can be decomposed in a way, right? And this is why we also evaluated for other data sets, right? So given, for example, that we would have perfect interpretability for cityscapes parts, it doesn't necessarily mean that just because we have perfect interpretability for parts, we also have optimal classification performance on cityscapes then. So obviously, there are still a few steps that are necessary to transform to parts to the actual output representations.
Mm-hmm. Okay, good. Another question again coming from the medical community is in medical applications, most often classification tasks are often done by first doing a semantic segmentation. And clearly what you're doing here actually with your semantic bottleneck is also some semantic segmentation.
Yes.
Does that relate? Is that really similar already?
Yeah, so in a sense, of course, so one of the crucial ideas is that if you're looking at interpretability, the one thing that is interpretable on any network is the output, right? So, and for us, it made intuitive sense to see that we can create such a sense, sub-networks that perform basically subordinate tasks, right?
Mm-hmm.
So not just classify the target domain, but see that we can potentially now segment like parts or other aspects, but leave this to the flexibility of the training, right? So that the network can choose it on by themselves. But I mean, so clearly there is a strong similarity in terms of the task, but the question, of course, becomes, right? So whether or how well we can apply the task to intermediate representations while retaining performance. So I think we have shown that this can work quite well.
Good. I'm very grateful for all your answers and all the questions. We now have to actually, due to some technical issues, switch to Zoom room, and we will be back in a minute. Okay. See you soon.
Thank you.
Okay, welcome back, and sorry for this very short break. We come to the third presentation of this joint session. This is by Lars Kammann, Stefan Menzel, and Mario Botsch from Bielefeld University, TU Dortmund, and the Honda Research Institute in Europe. This talk is now from the VMV. It's about how to transfer your triangle mesh into very nice interpretable patches. Please go ahead.
Yeah, thank you, Hendrik. Welcome, everybody. I'm happy to present our work on this compact patch-based representation here. So this work was done by Lars, who was a PhD student in my group in Bielefeld. I recently moved to Dortmund. The project was funded by the Honda Research Institute Europe, and Stefan Menzel was our collaborator on this side. Unfortunately, Lars quit his PhD and left academia for a serious job. So now it's my pleasure to give this talk and present his work. So let me first motivate what we wanted to do in this project. So we wanted to come up with this novel sparse geometry representation for three things: for understanding the design intention of man-made technical models, but also for manipulating and learning them. Now, this, what I present here, is basically the first part in an unfinished PhD. So it's basically, it stays with understanding. But the idea was to find something that you can also manipulate and use for learning by co-analysis of a shape family. So in this presentation, what I want to show you is a representation where you input a triangle mesh of some technical model, and the output, the encoding, is compact. So it's a sparse set of parameters, and these parameters should be geometrically intuitive, with the motivation that this would be easier for a human to manipulate later on and for a machine learning algorithm to learn and fit to data. So what we want to do is it's both an encoding and the corresponding decoding, or you can also call it analysis and synthesis. So given an input triangle mesh on the lower left side, the first part will be segmented into patches of constant curvature, so constant mean and Gaussian curvature. So the curvature tensor is fixed for each patch. We then extract the boundaries in between patches, the boundary curves, which we represent by Bézier curves. And then we take the connectivity of this patch layout to an aggressive decimation to get this minimal connectivity graph. This will then be the representation that we store or manipulate. And then the decoding phase loads this, reconstructs the boundary curves first because they are continuous Bézier curves, and then triangulates and remeshes the individual patches and optimizes their curvature to come up with a model that geometrically is very close to the one on the left-hand side. But so this is not a mesh compression. There's a completely different triangulation because we have the remeshing step in between. But this is the idea, to basically take a mesh and encode it by patches of certain curvature values and their boundary curves. So related work, I just mentioned it very briefly because we are already quite late. So you can find more details in the paper. So the encoding part is basically segment something into patches, and it goes back to the seminal work of Cohen-Steiner and colleagues, where they do Lloyd clustering on the geometry, like similar to k-means for arbitrary data. This was then later extended from planar proxies to proxies of different kinds. So planar parts or parts of cylinders or spheres by Wu and Koppel in 2005. And then the work probably most related, most closest to us is by Lavaux and colleagues, who also use technical models, do a region growing to find patches of constant curvature, and then basically approximate boundary curves and patches using subdivision curves and subdivision surfaces. So while Lavaux and colleagues do a region growing, we follow the approach of Wu and Koppelt, which is basically an extended version of the Lloyd clustering of Cohen-Steiner to find the different patches. Now for the decoding phase, what we have to do is optimize vertex positions such that the resulting curvature meets the curvature that we had in the beginning. Then we make use of the approach, the fiber mesh approach of Andy Nealon and colleagues, not their modeling metaphor, but their optimization, also the curvature-based processing of Michael Eigensatz and colleagues. And finally, for developable surfaces, there's a nice paper on discrete developability by Odenstein and colleagues from 2018. So those are basically also our ingredients for the decoding phase. Now, let me first talk you through the encoding and then through the decoding before I show you results. The first step in the encoding is that we take the input triangle mesh on the left-hand side and we find sharp feature edges, just edges in the triangle mesh where the dihedral angle is above a certain threshold. So this is not super critical, it just guides the segmentation by initializing the patches that we have. And then the main part is segment the mesh into patches of constant curvature, which are only planes and spheres and cylinders, which is somewhat intuitive, but it took us a while to find a paper that actually proves it. So we detect those three kinds of primitives. We closely follow the approach of Chanba Wu and Life from 2005, which is k-means or Lloyd clustering. So the idea is we have seeds. So in the beginning, we place one seed triangle for every of these regions you see on the left-hand side, separated by the sharp feature edges. Once you have the seed, you do a region growing So you assign triangles to the seed triangle it's closest to, and closest in this context means smallest distance or geometric distance to the corresponding planar, spherical, or cylindrical proxy. So once you have this partitioning through the region growing, you optimize your proxies. So you refit a plane or a sphere or a cylinder to the set of triangles. So basically we fit all three of them and take the one that gives the best match. And this is iterated in a k-means fashion. So for details, please see our paper or also the work of Java and Live. And then what we get is shown on the right-hand side. So we have here planes in orange, cylinders in blue, and there's no spherical part. But we get a nice, excuse me, nice and robust segmentation. Even though if you look on the left-hand side, the mesh is quite poor. So we have no inner vertices in these patches, which for other approaches is problematic because it's not robust to compute the curvature in these regions, because curvature you typically compute on the vertices. The vertices are not in the interior of a patch, but on the interface between two patches. So there's no robust way to detect the curvature in the interior of this part. But through fitting planes and spheres and cylinders, this works nicely. So the next part, now that we have the patches, is that we extract the corners. Corners are basically vertices that are incident to 3 or more patches. And then we extract the boundary curves in between two corners, which is basically a sequence of edges in the mesh. To each of these boundary segments, we excuse me, we then fit a Bezier curve in an adaptive manner. So we start with linear and they'll go up to quadratic, cubic, up to quartic. And what we do is we basically uniformly sample a boundary segment by arc length and then fit a Bezier curve. And if quartic is not sufficient, or if the topology is a closed curve, as you see here on the spherical part on the left-hand side, we split this up into several Bezier curves. So it would be more clever to fit a rational Bezier curve, because those can exactly represent conic sections like these, the circle you see on this curve here. We didn't manage to do this due to time constraint, but just fitting regular Bezier curves also worked quite well here and is significantly easier to implement. So once we have the curves, boundary curves approximated, then we go on and basically distill what we have to the bare minimum to extract the connectivity between the corner vertices. So we do a super aggressive decimation of the triangle mesh that you see on the left-hand side. We don't stay with triangle meshes, we produce a polygon mesh. So the connectivity graph that we get is shown on the right-hand side. It's basically, it preserves, the decimation preserves the topology of the boundary curves. So basically the circle that you see here just becomes a single triangle. And otherwise it ends up as a coarse polygon mesh, which we do with our PMP library, which implements most of the stuff that you need for this already. And then this is basically the encoding part. So what we store is this coarse connectivity layout. So the vertices, the corner vertices, their connectivity, which is just a coarse polygon mesh. Then the control points of the boundary Bezier curves, only the inner ones, because the start point and end point are the vertices, the corner vertices. And then for each patch, we store two scalars, the mean and Gaussian curvature. And this is the encoding. And then let's see how we can decode the mesh from this compact representation. In the first step, we load this coarse mesh on the left-hand side. Then we know for every edge corresponds to a Bézier curve, which we then just sample. So we refine every edge by sampling the Bézier curve and just inserting points here. So this, I don't know, many gone then becomes a many more gone. So we have like faces with lots of vertices. We then triangulate those and remesh it using either uniform or adaptive remeshing. So the images shown here is just uniform remeshing, but we know the target curvature that we want to achieve. So you could also go for a curvature adaptive remeshing. Also, this is based on the PMP library. So while the mesh on the right-hand side already looks quite good, you see some dents in this cylindrical part here, and this is because we didn't optimize the position of the vertices in any way. It's just a pure remeshing. Now the next step is, basically, if you look, I hope you see my mouse pointer. If you look here and then here on the right-hand side, the cylindrical part changes, and we do this by optimizing the position of the vertices to meet the curvature values that we stored for each patch, which is a combination of the fiber mesh approach of Andy Nealon and the curvature-based processing by Michael Eigensatz. And let me just jump over this. If you want to know details, just ask me later on, but for time reasons, I just skip over this. We first optimized just for the mean curvature. This is this part here, using alternating optimization. Then we also add the Gaussian curvature. This comes down to a to a nonlinear least squares problem, which we solve using the Ceres solver, which is quite nice. So worked very well in this project. So this already gives quite good result, and then we figure out that cylindrical patches or patches where you have Gaussian curvature of 0, so developable patches like this cylindrical part on the left-hand side, visually because of the meshing don't look so nice. And then we apply the discrete developability optimization of Stein and colleagues to get straight ruling lines, which you see on the right-hand side here. So basically the vertices are changed so that the edges nicely align with the direction of minimum curvature. And this is the decoding. And now let me show you some results. So for all the results, you see the input on the left-hand side, the resulting patch segmentation and boundary curves in the center, and then the result after decoding on the right-hand side. We see the number of integers and number of floats that we need to store for the initial mesh, and on the bottom row, the numbers that we need to store for the reconstructed, basically for the one in the center for our encoding. The compression rate is not great because the meshes on the left-hand side already are very coarse. The important part is that the Haushoff error is within reasonable bounds, and it's bounds that the user can prescribe. So for the segmentation part, we have an error threshold, and whenever we use more and more patches until the error threshold that the user prescribes is given, and this was something like 10 to the minus 3 around this part for the models I'm about to show you. So what we clearly see here is that on the right-hand side, we have a completely different triangulation than on the right-hand side. On the right-hand side, depending on your preference, the cylindrical part might be well enough represented with this piecewise planar quad strips, or it might not. We reconstruct the continuous curvature values, and we could, up to an arbitrary precision, remesh this thing and get you closer to the true cylindrical shape. Just some other models. I don't know, there's probably not too much to say. The compression rates, again, because the initial mesh is very coarse, are not impressive, but that's not the main point of this representation. Another model And you find all the details in the paper if you want to look closer at these different models. So the fan disk model, I mean, this is different because it's not a very coarse mesh, but a, I don't know, more denser mesh. And then the compression rates become reasonable if you like compression. So basically our representation depends on the geometric complexity and not on the initial meshing. What about timing? So the encoding phase, this is like very fast, not very hard to implement. The decoding phase requires this two-step nonlinear least squares optimization. This is a bit more demanding and takes, I don't know, about 10 seconds up to 30 seconds for the models I showed you. Then I mentioned in the beginning that the closest approach to ours is the one of Lavaux et al., who compute curvatures per vertex and then do a region growing to find regions of constant curvature. And their segmentation, like the input is on the left-hand side, their segmentation is in the center. And if they don't have vertices in the interior of a patch, they split edges or insert vertices in triangles, but those are inserted on the triangle plane. So you get zero curvature in these regions, which somewhat messes up the segmentation. And we don't have to do this. We don't have to touch the input mesh and get a more robust segmentation. And in the end, our base mesh is also like for the fan disk about 50% of the vertices and faces compared to theirs. So let me conclude. I showed you a sparse geometry representation that in the end takes a mesh and distills it to a small number of geometric intuitive parameters, gives us a rather compact encoding. This was the understanding part of a 3-year project where it goes about understanding and manipulating and learning. So future work could be basically the manipulation and the learning. If you apply this to a whole family of structurally similar shapes. And another part, of course, would be extend this to regions of non-constant curvature. So this, if patches have non-constant curvature, our approach does not perform very well. So this is clearly a topic for future work. We want to thank a couple of people like Moritz Kammann, Bernt, and Ullrich for discussions on like regions of constant curvature and how you could prove that this is only plane spheres and cylinders, and to Honda for making this project possible by funding it and by collaborating. And you for your attention. Thank you.
Thank you very much. Yeah, there's one question in the audience. Is the scaling consistent with the feature of the match? That is concerning the number of vertices versus faces and the number of curves. So
I think I don't get the question.
Yeah, that is, does the scaling and the overall time complexity you put in sort of like behaves more linear, quadratic in these numbers, basically?
Oh, that's a good point. Okay, let me go back to the timing slide. That's a very good question. We didn't analyze this for the I don't know. That's the correct answer. I don't know what the complexity of mesh decimation and all this Lloyd clustering is. It's so fast that we didn't care about. For the decoding part, this is something where you should care about because it takes longer. So it's this nonlinear least squares optimization. So this is complex, and the complexity is not so much dependent on the number of vertices because of the input mesh, because we remesh it anyways. The meshes that take longer because the nonlinear optimization takes more iterations. And it takes more iterations because the coarse patches that we produce and then remesh are geometrically more distant or more different from the patches that we want to have. So the nonlinear optimization has to work more. And I would guess, just looking at these models, this should depend on how many non-planar patches you have. So the more cylindrical and spherical parts you have, the more the nonlinear optimization has to do. That would be my guess. But I don't have asymptotic complexities.
Good. Overall, I mean, it's amazing that the encoding part is actually so damn fast. That might be because you're sort of already assuming that you have a CAD model. How would that actually behave if you would go for a scan of something that was originally produced by a CAD model? Is there any chance that you get also a decent representation out?
We tried it with scans of non-CAD models, okay, and it miserably failed because the patches are not of constant curvature. Mm-hmm. The test that you just mentioned, we didn't do, but that's a good point. We should have done this. We had some models that are not as clean as the synthetic models that you see on this slide. And you might get a bit more patches than you want to because the initial segmentation maybe doesn't work so nice. But overall, the method works okay because you average out noise by fitting a cylindrical part to something that's a noisy cylinder. So in the end, you don't reproduce your noise, but you get rid of it, which is what you probably want.
One more question. Overall, it would of course have been nice if one gets a canonical representation of a surface, which probably by initialization of your k-means and Lloyd approach already probably will converge to some slightly different segmentation into patches. Is that, are there some ideas of how to fix that?
No. That's the short answer. You're right. So if we take the same model and we just remesh it, so we have 5 different versions of the same geometry. Mm-hmm. We didn't test this, but I would guess we get 5 different representations in the end. Okay. Yeah, that's true.
Good. Then thank you very much, and we should go on to the last presentation. This one is a special presentation celebrating the 10th anniversary of the VCBM conference series. And the speaker is Timo Ropinski from Ulm University. You have the floor, Timo. And you should probably enable your video as well.
I will. Can you hear me now?
Yeah, we can already hear you. And
okay, great. And you can see my slides, I hope. Okay. Yeah, great. Okay, so welcome to this presentation, which is a very different one compared to the paper presentations we have seen earlier. It's about the 10th anniversary of VCBM, which is one of the co-located events here today. And I'm going to present a few things about VCBM as a chair of the executive committee. And I will start a little bit with the history. But so how do you actually celebrate the anniversary? Usually you buy a present. And when you look at a famous retailer, which also happens to be a sponsor of this event, this is what you find as presents for 10-year-olds. And, you know, I found it a bit techy maybe. So I was thinking, okay, what to do? And I realized, well, 10th anniversary in this case doesn't mean really it's a 10th birthday, because VCBM was held as a biannual event in the beginning. So in fact, we are at the 13th birthday. Unfortunately, it doesn't improve, right? So 2 out of the top 5 presents down here are still the same. You could say this is mildly interesting, but I thought, okay, we do something else. So looking into what VCBM is since the beginning in 2008 a Eurographics event. And when you go to the Eurographics website, then you see this list of events here. And when you actually scan through them, there are some events which stand out in one way or the other. The first two events which certainly stand out is the Eurographics annual conference, like the main Eurographics event, and the Eurovis conference, the conference on visualization, which is at the moment of equal size as the Eurographics conference. But there's also other events which actually stand out. And these are these three events. Yeah? When you look at the workshop on graphics and cultural heritage, urban data modeling and visualization, and visual computing in biology and medicine, you realize that these three events are the only ones which are not dedicated to a certain technology or methodology, but also to a domain. Yeah? Cultural heritage, urban, and biology and medicine. So when you track back the history of these three events, you actually figure out that these two are from 2013 and 2016, and VCBM was in fact the first one in 2008, which was considered or recognized as a Eurographics workshop going into a domain topic. And here you see the editors of the very first VCBM, which was Charles Botha, Gordon Kindelman, Wesley Neeson, and Bernard Prime. And the person in Eurographics who made all this possible was Heinrich Müller. He was actually in big support to go to this, let's say, a bit exotic way to get a domain workshop into the Eurographic events. So how did it all start? It started as a GE working group, the German Society of Computer Science. And the working group was initially called Medical Visualization, and it was founded by Bernard Prime and Christian Hege. And that was kind of the predecessor to make it a real working group, what we call Fachgruppe, and what we have today. And this is from 2003 to 2006. So in July 2007, Darkschnur seminar on scientific visualization was organized by David Ebert, Hans Hagen, Kenneth Joy, and Daniel Keim. And from that workshop, I took this picture. As you know, Darkschnur always puts these nice pictures on the website, and they are, of course, still available. And when you look at it, you see a lot of people on there. Many of them you probably know. They are still very active in the visualization community. And as it happens, Bernard Prime and Hans Christian Hege were also attending, as you might not see on the first impression, but if you scan a little bit, you will find them. And as Bernard was telling me about the story a bit about how VCBM happened, at that workshop, they met Charles Botha. So Charles Botha was back then assistant professor at TU Delft, and he was also very interested in medical visualization. And everybody who knows Charles knows he's a person who gets things done. And so they were connecting all together, and they were very keen on actually forming a new workshop on a European level on the topic of visualization in. And then the question was medicine, biology, both, what should it be? So Bernard essentially is a medical visualization guy still today. So he brought in the medical. Hans Christian Hege was always interested also in biological problems, so that was another domain. And presumably Charles was kind of bringing this together and suggesting, okay, let's do visual computing in biology and medicine, which turned out to be a very successful concept until today. When you look back, what happened in the last 13 years with VCBM, naturally the first location to have it in Delft in 2008, where it was organized by Charles. And then it went in 2010 to Germany. It was organized by Dirk Bartz in Leipzig. From then it went to Norrköping, where I had the honor to co-organize it with Anders Innemann. In 2012 and 2014, it was organized by Katja Bühler and Ivan Viola in Vienna. So that was all very successful, that we then decided, okay, this should not be a biannual event, but we should make it an annual event. And from then on, further locations in Europe happened, or were there on the map where VCBM happened. And as you know, today we are here again back in Germany for the third time in Tübingen. I can already let you know there are some white spots. We are eager to fill them up. Next year, we will be in Paris, in France. It will be organized by Mark Baden, and you will hear more about this at the end of this conference. So how did we select these spots? Well, obviously they are in Europe. That's important for us, and we would like to have a bright variety of countries in Europe involved. But also the location matters for other aspects. So VCBM is cross-disciplinary, right? So we are technology people working on domains, and for that we need to have the domain knowledge in there from medicine and biology. So we were always in favor of locations with dedicated clusters. So in Delft, where VCBM was for the first time in 2008, the Delft Health Initiative was founded only in 2009, so 1 year after VCBM. But of course, there was already a lot of collaborations and projects going on in this area. And the Delft Health Initiative sounds like a blueprint for what the idea of VCBM is. It integrates science, engineering, and design for sustainable healthcare based on innovative technologies. So this is something we can very well relate to and which we see as a good benefit or cooperation synergy for VCBM. Similar in Leipzig, there's an innovation center of computer-assisted surgery, a little bit more specific to a certain branch of medicine, but also computer-aided techniques are in focus. 2012 in Norrköping, we were co-located with the Center of Medical Image Science and Visualization, CMIV, many of you probably know. They develop future methods and tools for image analysis and visualization for applications within healthcare and medical research. So also a very good fit for VCBM. Bremen, Fraunhofer-Mewis, also well known. They focus more on software solutions, which is also a nice fit. And also in Bergen, where the Mohn Medical Imaging and Visualization Center was recently founded. It was previously known as MedVis, which was a co-located conference for the VCBM in 2016. These are just a few examples I wanted to pick out to emphasize that it's for us always important to collaborate with domain people at the locations where VCBM is held, which is of course challenging to find every time, but we always found it very successful to do it in the end. Besides location, also co-location matters. So sometimes we are actually trying to have it co-located with certain conferences. I mentioned the MedVis conference in 2016, where medical professionals meet. The MICAI conference, which is as VCBM on the border between medicine and technology. And this year we are co-located with VMV and GCPR. And in the future, of course, we would be very happy to be co-located with other similar events. So to get all these things organized, we have formed a steering committee over the years, which oversees the organization. And this is formed by Ingrid Hotz, Helvig Hauser, Barbara Kotzlikova, myself, and Anna Villanova. And we are very proud of the gender diversity we have in this committee, which makes it very fruitful discussions and brings up the conference to a good track. So just recently, beginning of this month, we have now a charter for our steering committee. And why I bring this up, because it actually has a lot of information on how to organize future workshops. So if you are interested in the future to organize a VCBM workshop, then this charter might be a first point of information to look at how the process is. And of course, you can also contact me in order to get more information on this. So what content categories do we have at VCBM? If you've looked at the program this year, you will already know there's a variety of tracks. We have full papers, of course, keynotes and panels. But since 2010, we also have tutorials, as we have seen yesterday, for the visualization with Unity. We have short papers, and since 2015. And since last year, we actually have an image contest as well, which I find also a very nice track where you can actually look at very beautiful images which are produced. So Michael in the opening today has shown this rendering of the coronavirus, and these are all images which contribute and come out of VCBM. So the question is, what topics do we actually look at? And what we have analyzed the session names of the last 10 VCBM conferences. And what you see is a few sessions here emphasized based on frequency are more often, I would say one obvious thing is like volume visualization, which is one of the branches MetVis started with. But you can also see the bio part is emphasized by molecular visualization, networks in biology, for instance. And then what you can also see, we really cover the full spectrum of visual computing, where we have segmentation, but we also have visualization, and we have further tracking and even simulation tracks in our conference. So if you look at the program in 2021, 2020, it should mean here, you see we already have a lot of VR applications in. So we are evolving our topics, and we are always keen to get new contributions from different topics we haven't covered so far. So who's all working on this? I've looked a little bit into previous proceedings and papers. And so it turns out we have 679 unique authors until 2019 so far. And when you look at it a little bit closer and analyze based on the frequency, then it turns out that roughly 10% of these authors have more than 2 papers, and roughly 90% have 1 or 2 papers only. Yeah, and so you see some names which are well known in medical visualization, which publish frequently at the VIS conference, and for them the VCBM workshop still seems to be an important outlet for their research work. So this is something which makes us very happy. To give some examples of what actually is published at VCBM, I've selected the 3 most cited papers of the previous VCBMs, and this is most cited normalized over the years, right? So otherwise they would be all from 2008, presumably. So the first one I would like to talk about is from Gasteiger and others. It has been published in 2010, and this is something I would call a standard visualization, medical visualization paper, where a visualization technique is suggested in order to communicate flow within an aneurysm. So here you see flow patterns, and this is the shape of an aneurysm. And as you can see, the previous standard approach of doing it by just exploiting transparency with alpha blending didn't really communicate the shape of the flow in the context of the aneurysm pretty well. But with the elaborate pipeline they have suggested in their paper, they can actually come up with a picture which is conveying the structure of the flow much better. And they have analyzed it, and apparently in a very convincing manner, as the citations of this paper suggest. From visualization, we can go to analysis. So this is a segmentation paper from Simon and colleagues published in 2008. It's about statistical shape models for segmentation of pelvic bones. And here you can see the different parts. And this paper has a really thorough analysis of the segmentation results. They present different error metrics, but also present good and bad cases, and it's very thoroughly written. So no wonders that this is also a very highly cited paper. So these were two papers which were more on the medical side of things, but we also have plenty of papers which are more on the biological side. And this is the most cited paper actually normalized over the years. This is CellView, which has been published in 2015. And it has more than 12 citations every year, which I find is a very good number for a workshop. And what they propose is actually how to generate illustrative and multi-scale renderings of biomolecular data sets, like the coronavirus we have seen in Michael's presentation earlier today. So the challenge is there that you have a lot of structures contributing to this overall impression. And so what they do is they borrow from graphics to realize level of detail rendering techniques, and then they can visualize crowded environments of cells. And this is something which was highly regarded also outside of the core visualization community by biologists and other domain experts, which actually facilitates this technology. So all these papers are nicely cited, and we are very happy with that. This is also due to the fact that the 3 best papers are actually invited to submit the extended version to the Computer Graphics Forum. And this was established already in 2014. And Helvig Hauser, who's now also a member of the steering committee, was very helpful to further bring on this process. And since 2018, we also have a special session, a special edition of Computers and Graphics, where people can publish their work. We not only do hard science, we also, of course, do socializing, not just drinking, but also sports, culture, and singing events. So if you haven't attended a VCBM, and this is your first time this year, we hope that we will see you also in the non-virtual conferences in the future. So towards the end, I would like to bring up a few things of people who have actually left the VCBM organization. And we decided 10th anniversary is a good reason to start with awards. And the first awards we give out in this line goes to Barbara Kozlikova and Renata Raidu for their local organization of VCBM 2019. So VCBM 2019, whoever was there, was an exceptional event. So it's a good time to start the award with this. And I really would like to thank Barbara and Renata for their engagement in there and for all the work to make this a great event. Thank you so much. We also have 2 people who left the steering committee recently, Katja Bühler and Hans-Christian Hege. They also contributed massively to the development of VCBM. It was always great discussions with them, and we would really like to thank both of them for their services as a VCBM steering committee member over the years. So that leaves one last thing, and this is giving out a very special award. Everybody who's involved in VCBM knows Bernhard Prime relentlessly over the years has pushed everything forward, connected with Eurographics in the beginning, helped shape VCBM, and was really like, I would say, the single leading figure in this so far. And for that, we would like to give him out a very special event here, for being the chair of the VCBM steering committee from 2013 to 2019, and for building and shaping the VCBM workshop over the years. So thank you very much, Bernhard, for all this. And I think also in the name of many researchers who published their work at VCBM. And with that, I would like to close and congratulate EG VCBM. If you would like to get involved, simply attend the sessions, connect through Twitter, or contact the steering committee. And I would like to thank David Schmidt and Sigrid Duschek. They have helped with the stats I was presenting here, and Ingrid Hotz and Bernhard Prime have contributed some of the photos we have seen. Thank you very much.
Thank you, Timo, for this very nice overview of what has happened during the last years, the 10th anniversary of VCBM. With that, we are now at the end of the first joint session of this triple conference. We're now going to have a break and continue at 11 o'clock. Actually, I would like to ask every speaker to already start joining the associated Zoom rooms, because after the break, the three conferences will have three separate channels to work with. Okay, thank you very much for your attention, for all your participation, and please enjoy and communicate with each other. Thank you.